All right, so to introduce Taylor polynomials, what I'm going to do is I'm going to show you a couple of functions. Essentially, polynomial functions can be used to approximate functions such as sine of x, e to the x, and natural log of x. So what I have here is I have already placed in my calculator, there it is, I have already placed y is equal to the sine of x, and in my y2, I have placed x minus x cubed over 3 factorial plus x to the 5th over 5 factorial in the calculator. All right? So what winds up happening if I do that, and if I look at the graphs, is we get, of course, the sine of x, which is nothing particularly interesting. What gets interesting is this upcoming part. What do you notice about that? Yeah, it overlapped. In fact, when it started to overlap, how good of an overlap did we have? Yeah, pretty darn good. Maybe not, I mean, it's probably off by a little bit. But if I were to look at this, I don't know, maybe if I zoom, let's zoom to just the decimals. All right, so this is -1 to 1, I believe -1, or I'd have to actually look at what the actual window is. So, you know, if we're looking at that particular window, that's -4.7 to 4.7. So that's a pretty tight window there. Basically, it's set up so that every time you click left or right, it always changes by 1/10. So if any of you have ever tried to figure out what zoom decimal is, there you go. But that's a pretty good match for that function in that region, isn't it? And what's going to wind up happening is there's actually a pattern to this particular polynomial. We'll see it later on. And if I extend that polynomial out a little bit, I can actually extend my overlap further and further out the more terms I add into this problem. Ideally, if I have an infinite number of terms, I'm going to create a polynomial with an infinite number of terms that will be a perfect one-to-one match with this sine of x function. Of course, that function isn't something that we just suddenly magically tripped over. That's not something that you know, somebody just said, hey, look, this. You know, I wonder what would happen if I take x minus x to the 3rd over 3 factorial plus x to the 5th over. I wonder what that looks like. Wow, that kind of matches with sine. There's a whole process to that, and that is by this Taylor and Maclaurin polynomial. We've got these two gentlemen. We've got, what's his first name? Brooke. There you go, Mr. Brooke Taylor, an English mathematician. We also have a Scottish mathematician, Colin Maclaurin, and as you can guess, if you know anything about the Scottish and the English, if you've taken AP Euro, you probably know they don't like them. If you haven't taken AP Euro, hey, they're two countries that are really close to each other that are kind of similar, so therefore they must hate each other, because you got to have something that differentiates each other, even if it's just a name. They also talk funny. No, they don't. Okay. Aye, that's right. I can go into my Scottish accent and get all excited about things. Anyways, so a Taylor polynomial and a Maclaurin polynomial, these two guys found these out about the same time, and they're very similar to each other. The difference is going to be what's called the center. And the center is going to be the spot that I want to originate my polynomial off of. A lot of times we're going to prefer a Maclaurin polynomial because it's centered at 0. And we know that 99.999% of the time, things are really easy at 0. However, there will be instances, and some of that comes down to some functions will work a little different than others, but there will be some times that I want to actually shift my center, and if I shift the center, I'm going to need to use the Taylor polynomial function. Again, it's the same concept. If you look at the Taylor polynomial function, you'll notice that I've got an f of c, I've got an f prime of c, I've got an f double prime of c, a triple prime, a quadruple prime. One of the things that you don't see here is this is over 1 factorial, and this is technically over 0 factorial. And what you can see here is that this is a 0 degree, or not a 0 degree, this is a 0 derivative. You'll have a 0 degree x, and 0 factorial is 1, so we don't typically write it. You'll notice the first degree, I keep saying degree. The first derivative also matches a first degree polynomial, which is over 1 factorial. The second derivative happens to fit the second degree polynomial over 2 factorial. Third, 3, 3. So you'll notice that n, and n. The derivative will match the power and will match the factorial. Another thing I want you to notice, these are all x minus c's. It's because if I'm centered, remember that this is an x center. So of course a minus c actually shifts us to the right. A plus c will shift us to the left. So we need to remember that we've got all of that. That's all well and good. One of the things I do want to talk about is naming conventions real quick. When we talk about a Taylor polynomial, we will call it one of 3 things. I will call it t sub n of x, or p sub n of x, or my personal favorite, I will call it Jimmy. Polynomial, or I'll call it the polynomial is. Or I just won't use a name at all. You are expected to use one of those 4 outcomes, t sub n of x, or p sub n of x, or the polynomial is. You are not allowed to use anything else. The naming conventions are incredibly picky here. Okay? Euclid? It's Euclid. Euler? No, you're thinking Greek versus Swiss. Oh, here we go, 45-minute hand clap. I'm going to start playing fits and the tantrums every time they do that. You threatened it. You must follow through now. Okay. So in a very basic sense, when I deal with a Taylor polynomial, they ask me to create a Taylor polynomial. What I would want to do is I'd want to realize, okay, this is a 3rd degree Taylor polynomial. So I've got p sub 3 of x. I'm centered at 2, so c is equal to 2. And if I want the 3rd degree Taylor polynomial here, we would have to have the f of 2 over 0 factorial plus the f prime of 2 times x minus 2 over 1 factorial plus the f double prime of 2, x minus 2 to the 2nd over 2 factorial plus f triple prime of 2, x minus 2 to the 3rd over 3 factorial. And I'm writing this out specifically as a longhand thing so that you can see what we're dealing with, okay? Because clearly I'm not going to leave it like that. I know what f of 2 is. F of 2 is 3. So I would write that, and I would just jump straight to 3. Over 0 factorial, which is 1, nothing interesting. So I'd call this 0 minus 4 times x minus 2 plus 7 times x minus 2 squared over 2 minus 5 times x minus 2 squared over, or cubed over 3 factorial. And you could also write 3 factorial as 6. So the idea is really this is nothing more than a lot, as long as you can memorize the general pattern to a Taylor polynomial. This is literally going to be plug and chug. Yes, ma'am?
Wouldn't it be like 2 factorial underneath 7 x minus 2 squared?
So the question was, is that going to be, I'm sorry, so that people can hear what your question is. So the question was, should that be a 2 factorial? Absolutely, you can write 2 factorial, but 2 factorial is 2 times 1, which is just 2, so I'm going to skip that. If you want to put the factorial, as long as it's a mathematically equivalent statement, that is fine. Now, this is, yes, Chip. How is 0 factorial 1? I will prove it to you on Monday. I have to actually go review my proof. It has to deal with the actual function that defines factorial and how we go through that. So there's a couple of proofs. Let me find one that works. It's been about 365 days since I've last had to prove it. And I do the proof and think, wow, I should really just memorize this proof. And then someone asks me that, and I go, let me go find my proof. Yes. So what I will do is I will show you a proof on Monday for that, and we can go from there. I love it. A bunch of people are like, prove it. No, it's not acceptable. Good old math class. Now, this is, of course, the beautiful God if they all were just that easy. But guess what? It's not always that easy. Traditionally, most of the questions we will deal with are going to be more like this second problem. Find the Taylor polynomial. So they're telling us it's a Taylor of degree 4 for f of x is equal to e to the 3x at 2. What I want to realize is that this at 2 is really, that's my center to my polynomial I'm creating. I almost called it a series, and that's technically not true. So that's my center to my polynomial. I want degree 4. What that tells me is that is my number of derivatives. Which means in this problem, not only do I have to have f of x, but I will need to find f prime of x, f double prime of x, f triple prime of x, right, and the fourth derivative of x. By the way, once we get past triple prime, we stop using primes because seriously it gets really dumb, especially by the time we hit like the 7th, 8th, or 9th prime. You really don't want 9 tick marks. So what we do is we put a number, we put a value in parentheses, and that is my derivative in function notation. Yeah, tick, 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 tick. So, if f of x is e to the 3x, then f prime of x would be 3e to the 3x. The next term will be, which we could write if we really wanted to, but I'm really lazy. 3 squared e to the 3x. Now again, it's not too bad here. The next term, again, not terrible, but 3 cubed e to the 3x, and the next term is 3 to the 4th e to the 3x. So to do an nth degree polynomial, I'm going to require that many derivatives, typically. Talk about that in a minute. And then if you look, it doesn't say f of x, f prime of x, f double prime of x, f triple prime of x, f fourth derivative of x. It wants each of those evaluated at c. So now I need to find out what is f of 2, f prime of 2, f double prime of 2, f triple prime of 2, fourth derivative of 2. So, f of 2 to the 6. Luckily, this actually proves to be fairly simple because each one of these really just changes the e from e to the 3x to e to the 6. But wait, there's more because we haven't answered the question yet. The question didn't ask us to find all the pieces to make the Taylor polynomial. It asked us to actually write the Taylor polynomial. So the pattern is we start off with the 0 derivative at 2 e to the 6. Then we'll take the first derivative, 3e to the 6, multiply that by x minus 2, x minus the center to the first power, technically over 1 factorial, plus 3 squared e to the 6, x minus 2. This is part of the reason why I like this is that e squared, it keeps track of everything, over 2, plus plus 3 to the 4th, e to the 6, x minus 2 to the 4th over 4 factorial. Okay. By the way, you will notice that on a lot of these notes, there will be a statement about TI-89s. That is the person whose notes that I'm utilizing, Miss Stevenson's. You may all recall her. These are Miss Stevenson's notes at her school that she taught at. They had TI-89s. Some of you go, that's nice. I would have loved a TI-89. I don't know. The TI-89s can be a bit of a beast to learn. But one of the things the TI-89 can do that ours cannot is that the TI-89 has what's called a computer algebra system, and it's actually able to create a Taylor series for us. Actually, a Taylor polynomial, which is pretty awesome. Yeah, we get kind of ripped off there. That's lazy. And what have we said about mathematicians, Kevon? Mathematicians are inherently lazy and try to do as little work as possible to get the correct solution. All right. Hey, you know what? It was fun finding a fourth derivative. We should do a problem that requires a fifth derivative. Find the Maclaurin polynomial of degree n equals 5 for f of x equals sine of x. I have a bit of a problem. What's my center? 0. Why? It actually is not that it did say. It says that this is a Maclaurin polynomial, and this implies that our center equals 0. So Maclaurin is always going to be a center equals 0. It will never change, which is helpful. So we need f of x, f prime, f double prime, f triple prime, the fourth derivative, and the fifth derivative, because that looks like fun. Now we actually are, I'm personally okay with this, doing a fifth derivative of this particular question, because the derivative of sine is cosine. By the way, for those of you who thought you were going to forget your derivatives, you're back. Second derivative, negative sine, negative cosine, sine, cosine. And I want to evaluate f of 0, f prime of 0, f double prime of 0, f triple prime of 0, fourth derivative at 0, and the fifth derivative at 0. Whew. What is the sine of 0? F prime of 0. Negative sine of 0. Negative cosine of 0. Sine of 0. 0. Cosine of 0. This is why we like this. So, if I want the fifth degree polynomial of x at the center of 0 for sine of x, we would have 0 plus 1 times x over 1 factorial. Notice that it's now x. It's not going to be x minus 0, obviously, because that just seems silly. Plus 0 times x squared over 2 minus x cubed over 3 factorial plus 0 plus x to the fifth over 5 factorial. I actually cheated and forgot to write the x to the fourth over 4 factorial. I apologize. Or, rewritten a slightly different way, x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, which should not be a surprise, since that was the function we looked at the beginning of the day. Ladies and gentlemen, x minus x to the third over 3 factorial plus x to the fifth over 5 factorial is the fifth degree Maclaurin polynomial to the sine of x. By the way, that is a Maclaurin polynomial that you will be expected to memorize. You will have to recall 4 Maclaurin polynomials as we go. We will talk about this. I believe I introduced this on Wednesday next week. You will need to have memorized, and if you look on your yellow cardstock, you'll notice that there's a spot for each of them that says Maclaurin series. You'll need to memorize the Maclaurin series for sine, cosine, e to the x, and 1 over 1 minus r, which is the geometric series. Okay, so the question was, if the degree increases, will that make it match a little bit better? The idea behind that is yes. As it stands right now, this is actually not going to be a one-to-one match. As we saw, it's off a little bit. There will be a location where these will match. Right now, where's the only location where this polynomial will be of x minus x to the third over 3 factorial plus x to the fifth over 5 factorial? When will that match the sine of x? It'll match exactly at 0 because that's my center, and I'm forcing those two to be equal right there. That's the significance of our center. As I add more terms to my polynomial and I expand this polynomial, I will get a more and more and more accurate match of these. And then what we're going to do is we're going to start taking this to a logical extension. If I can have a lot of finite terms, why can't I have an infinite number of terms, thus turning my Taylor polynomial into a Taylor series? And once I get to a Taylor series, I can start investigating when does this converge with the original function. And I can start looking for things like that. And that really is the progression that we're going to be processing through. So you're already looking down the road, which is where I want you to be looking. All right. Real quick, just so you can see how good of an estimate just a 5th degree Taylor polynomial is. If I were to investigate this particular problem at 1.4, the Taylor polynomial will give me a value of 0.987 compared to the actual value of 0.985. For the vast majority of, say, industrial problems, being within 2 1,000ths, I'll take it. You can see that there is, and you'll notice that there are some spots for you to jot down these numbers. You'll notice that there's an error of about 2 1,000ths there. That's just, there's a very, very small separation. We saw that on the graph. It's really close, right? However, if I start expanding this, and I start looking further out, you can see that eventually we start seeing some. Now at 2.1, this still isn't a terrible split. You're looking at a little over 3 100ths, 33 1,000ths, which is not necessarily bad. Why is this a worse estimate than the previous one? We're further from the center. The idea is as I expand further and further from the center, if I were to take this even further out, I mentioned at 2.7, yeah, from 1.4 to 2.7, that's suddenly 2.7. I got problems with that now. Now I've got a fairly significant error. How am I going to create a better estimate for this? I'm going to have to increase the number of terms, which, as we start thinking about that, of course, that's going to require a little more work. It's going to require a little more effort. And you start, as an engineer, if you're those of you interested in engineering, start thinking about that. I need to start weighing how much work am I going to do to get how much of a better answer. Or could I just shift the center at that point in time? Wait, we can do that? Of course we can. This is math. We're allowed to do a lot of things. Cool? All right. Again, today is just a mechanics day. There's nothing crazy going on. So other than the fact that the mechanics are kind of weird. So what I'm going to have you do is I'm going to have you work on the very first worksheet that's connected to this. It's worksheet 1 on Taylor polynomials. It's just a mechanics sheet. There will be a little bit of kind of playing around with it, but you will be able to get through that fairly easy, followed by a FRQ. You'll notice that there's going to start being a lot of FRQs tacked on to some of these questions. You'll notice this packet is rather large. You've got worksheets, and then you've got an answer key, and I left the back of the answer key blank just so that it's kind of a little more organized, which took a little extra paper. But yeah, there's also 20 pages worth of stuff in that packet too then, which is why the pink packet is so big. So we're going to start with that. We'll do mechanics. Tomorrow we'll start learning how we can assess things like maxes and mins utilizing Taylor polynomials, which was really cool. I enjoy those. Those are pretty nifty. Absolutely coming in on Saturday. At this point in time, what's more important, biology or calculus? With the calculus, you can describe all of the biology. All right, folks. Go ahead and use the rest of the period to work on these questions, and yeah, we'll go from there.